My name is Gillian Goward. I'm a professor of chemistry at McMaster University in Hamilton, Ontario, which is in Canada. The most important thing that has evolved in our group and in others is the ability to look not at one material at a time using what we would think of as an ex situ experiment, either of a pristine material or of a material that we extract from a battery, but moving toward in situ and now what we call operando measurements of the cell while it's being cycled in the spectrometer. And that's been an evolution in the last 15 years or so, maybe even longer. But when I was a graduate student, certainly we were only doing sort of standard magic angle spinning experiments of pristine materials and looking at them one at a time. So for each sample, you needed to run a battery, extract the material, run the NMR spectroscopy. The advantage of that is that you can do magic angle spinning, and so you get high resolution spectra relatively easily, even if the system is paramagnetic. As a solid state chemist, diffraction is the first method that we always go to synthesize a material and check whether it's pure. But we found, and many others have found as well, that NMR is sensitive to things that the diffraction experiment can't see, and particularly with an isotope like lithium, which is very light. The starting materials, for example, might not be visible in the diffraction if they're left as amorphous residues, but in the lithium NMR spectrum, they're very obvious. We use NMR both to look at species that aren't easily detectable by diffraction, but also really importantly to look at species that are mobile. And NMR is quite uniquely suited to looking at mobility as compared to a diffraction experiment, for example. In lithium-ion battery materials, knowing where the lithium sits in the structure is the first piece of information, but the second piece of information is where does it move, under applied potential or under the change in the synthetic parameters, what are the exchange processes or what are the dynamics of the lithium-ion. Early on we were looking, and we still look at both fuel cell materials and battery materials. So I was interested, I don't know, from high school already in questions of energy storage and energy use as a society, and knew that I don't think I had any premonition or anything. It was simply that there was interest in alternative energy forms. Solid state chemistry is actually a really important aspect of alternative energies, because a lot of the structures that we use in battery materials, but also in solid oxide fuel cells, rely on redox active ions in a particular lattice or framework, and understanding that structure is really important to then predicting the performance of the device. So we have always had an emphasis on that aspect in the group, whether it's in fuel cell materials or in battery materials. And it was simply a matter of, as a young faculty member, wanting to have lots of different projects going on to see which would be the most successful. But consistently, the area that's had industry interest in our group has been on the battery side. We've had really good collaborations there and questions coming from industry colleagues to say, what can this technique bring that others can't? We love looking at the pristine materials because they tend to be well behaved and the spectroscopy tends to be beautiful. But with battery devices, as with many devices, the challenges come when the material is not behaving perfectly, or at the interfaces between a liquid and a solid, at all of the places where the spectroscopy gets more messy. Those are actually the places where there's important questions to answer. And so we've moved into the operando methodologies to look at things like concentration gradients that form in an electrolyte over time and under applied potential. And that's an important property in terms of understanding how a device will respond to an aggressive current, whether that's a charging process or an acceleration process, or how it will age and whether the properties will be consistent over time or not. So we've looked at a lot of ways of mimicking what that aging process looks like, whether using temperature or using drive cycle analysis, in order to then backtrack and say, okay, here's how we should model the behavior of this material in an actual onboard device. Yes, all of those. They're all interconnected. So when we try too hard to scale down the size of the battery, we make a sacrifice on the safety side if we end up with not enough material in the interconnects or in the components of the cell that protect it from overcharging and from short-circuiting, basically. If we think carefully about how much lithium there is available, sometimes we think there's not enough lithium. Other times, if you do a full analysis, it seems like there is. If our full society were to adopt lithium vehicles quickly, or lithium-ion battery-based vehicles quickly, we might have a problem. So I think that recycling is going to become really important. What drives the recycling industry right now is the cost of the materials you can recover. So right now we're good at recovering the cobalt or the nickel or the copper, but we're not so good at thinking about even how you would recover the lithium. And this is, I think, going to become an important property. But the other strategy is to move away from relying on lithium exclusively and consider sodium-ion batteries, for example, which are already growing for sure in commercial application and offer lots of the advantages of the lithium-ion battery, but haven't been as fully studied yet. One of the things we talk about in our group is helping consumers believe that the devices they're going to purchase are going to be safe and long-lasting. And one of the ways to do that is to have data sets that show that the phenomena that are happening in the battery as it ages are well characterized, and therefore this allows OEMs to provide warranties, to provide insights into how to protect the cell. Processes like lithium plating within the cell as it's rapidly charging are really problematic. As we lose lithium capacity within the cell, that will affect its aging properties. And so we aim to detect that lithium plating process as early as possible and then develop electrochemical strategies that will allow redistribution of that lithium within the cell and therefore improve the lifetime. And I think that this is one of the main challenges, that consumers aren't confident to make the leap into what seems like a more expensive opportunity as a vehicle because they're not confident that it will last. But if we can build up that knowledge of how cells respond under different conditions, and we can provide people who manufacture cells or even manufacture cars the insights into how those different materials choices affect the longevity, then I think that it will become a much more popular consumer product. And thankfully, we're already on that upswing, so that's really good to see. The main thing that I talked about this week at the Euromar was our development of the parallel plate resonator, which was done in collaboration with Bruce Balcomb's group at the University of New Brunswick. And it's a coil geometry that allows for more efficient filling factor of the active material relative to the coil volume, and gives really high sensitivity over a wide surface area. So this device is going to let us look at high throughput characterization of commercially produced electrode materials and detect this lithium plating phenomenon under different conditions. So we think that this device is actually something that other groups may be interested to use. It's actually quite simple to put together once you sort of have some know-how from the Balcomb group, thankfully. And we're aiming to use it for not just lithium, but also for other nuclei, so we can detect things like the electrolyte, both the salts and the organic materials that are there, and determine how they respond to aging conditions as well. Lithium batteries have been a focus for several years. Prior to that, we also have a body of work in fuel cell polymer electrolyte phenomena. What we're aiming to do next is sort of continue applying these kinds of strategies to different electrochemical systems. Lithium batteries aren't the only electrochemical storage technology, so we are also working on air-based cells, both zinc and aluminum air cells. There's also work in sodium-ion batteries, like I've mentioned. We're basically curious to figure out where NMR can help us to answer questions in electrochemical systems. What we need is to get away from grid-level distribution of electricity to more localized power installations, whether that's solar or wind, and with battery backup, that we not rely on these enormous grids and aging grid infrastructure, and allow us to get away from that. I do think there's opportunities in small modular nuclear reactors that are not being used because perhaps of an overabundance of caution, but that there's been lots of developments in that area that are exciting. Yeah. We have to get away from fossil fuels, and the faster that we can do that, the better. But I think it's not going to be one solution. It's going to be a range of different technologies that are needed.